Hello, my name is Rhodes Foster, and this is Physics 2211 Lab 2. Looking at a brief overview of what we'll be getting into, we have an introduction, data observations and models, some computational data, results and analysis, and then finally a conclusion. The purpose of this lab is to analyze the projectile motion of an object. This projectile motion will be compared to computational models of projectile motion with and without drag. For a little preview of results, gravity and drag are going to act as forces on a falling object that influence its motion. And the fundamental principle at work here is going to be Newton's second law, so the momentum principle. What is Newton's second law? Newton's second law is the momentum principle, and it states that a force is equal to the change momentum over change in time, or equal to m times a. This indicates the change of movement within the system and its surroundings. So again, F equals ma, or F net equals delta P over delta T. Some important terms here are gravity. The force of gravity is equal to mass times acceleration due to gravity. It's going to act as a force of attraction, pulling an object towards the center of a body of mass. And we are working with Earth here. Drag is a resistance force that acts against the motion of an object falling through the air or water, acting in the opposite direction of where the velocity is going. So the force of drag is equal to 1/2 times the density times the speed of the object times the cross-sectional area times the drag coefficient. The procedure of this experiment will be to record a video of an object being thrown in the negative xy direction. In this case, we're going to use the center of mass calibration stick and axis to record the projectile motion. Then we're going to create two computational models, one showing gravity's effect of the object and another showing gravity and drag. Then we're going to compare them and its relation to Newton's second law. Here we have our tracker data represented in a graph and an image of the experiment to the left. This is me shooting a basketball into a hoop. So we're starting where I shoot the ball and we're ending where the ball goes into the net. The arc of the basketball is represented by the shape of the curve in the graph, as you can see, moving in the negative x direction. Here we have some observations from the experiment. Of course, we started at 0 seconds at 0, 1.803, 0 meters with an initial velocity of negative 5.74, 6.54, 0 meters per second, and then we ended after 1.1 seconds. The system in this case is the basketball, and the surroundings are anything else that affected it. I then took that experimental data and inserted it into GlowScript. Again, this is without drag, so the net force is just going to be the force of gravity, so that is added here. Velocity update and position update formulas were also added, as we can see here. Right here, we have taken the data from the GlowScript and we made it into a nice graph. As you can see, similar to the experiment, the ball is going to follow the path that we see on the curve here. Then for the last part of this experiment, we included drag. I made B equal to 0.01, which is pretty fair for a basketball, and we included the drag force equation and net force equation. Here we have the graph that we netted from running that GlowScript from before. And as we can see, the y value has decreased a little bit, indicating that drag did indeed act on this system. We then combined these three graphs into one, and we can see that the model not taking drag into account shows its position falling further in the same amount of time since the object had nothing preventing it from fully accelerating. Getting into some potential errors, mistakes could have been made using the tracker software. Also, in the video model, it would be impossible to not have drag interacting with the falling object. So here, neither model will accurately predict terminal velocity because the basketball didn't fall long enough for terminal velocity to be reached. We could redesign the experiment where we would drop the basketball from a super large height, and it would reach terminal velocity when the force of gravity equals the drag force. So in this case, if the basketball was thrown straight up at that same speed, it would have a higher y component of velocity, and therefore it would take longer to decelerate to zero velocity before accelerating back down. In conclusion, the momentum principle, Newton's second law, is observed in the video model through the object's acceleration, mass, and force interaction. Force grows as mass grows, the same with acceleration. The drag model better exemplifies what is actually going on in the experiment, since the real-world object has to undergo drag force.